Hello, my name is Pierre Bichon. I am a PLM for Telco Cloud Solutions. Thank you for joining our topic number 1, Telco Cloud 101, the first of a series of webinars on Telco Cloud Solutions. But before going into Telco Cloud Solutions, let's have a look at some fundamentals on Telco Cloud to make sure that we start with a basic understanding on what is Telco Cloud. We will go through what network function virtualization and software-defined networking mean, even if we will not detail what OpenStack or Kubernetes are, nor how SDN works in detail, as there are other sources of information available on those topics. But we will explain what are the key aspects of NFV that matter for Telco Cloud. We will discuss scopes, or control and user plane separation, and what it means to distribute things across the telco network. And finally, we will say a few words on cloud native, the most recent trends in virtualization, and its impact on Telco Cloud. What is Telco Cloud? Telco Cloud is not a public cloud, but it uses some of the technology. Telco Cloud is not a data center, or not only a data center, as it is the telecom infrastructure that is virtualized. Telco Cloud is about delivering services using cloud technologies, whether the cloud is built by the telco or a third-party cloud is leveraged. As such, it has the telco specifics of guaranteed end-to-end reliability, SLA, security, and privacy. Service providers operate the telco cloud as they used to operate networks. In general, telco cloud enables the transformation of business and their digitalization. It is true both for the telco and its customers. Telco Cloud enables the virtualization of network functions in the form of VNFs. VNFs have some characteristics that come from cloud, such as multi-tenancy, general system QoS, or self-service, and some that are specific to a telco cloud environment, such as high throughput, high availability, or geo-dependency. Telco cloud network functions can be similar to cloud workloads. This is a case of control plane VNFs, such as the MME, the HSS, AAA, PCRF, or backend databases. But others are very specific when they address packet manipulation and forwarding. This is a case of user plane functions, such as a subscriber session management for wireline in a BNG, or in wireless in a mobile packet core, or even network security functions. There are VNFs that are a combination of traditional networking elements, such as firewalls, DPI, load balancing, proxies, such as CDN, or transformation VNFs, such as transcoders or security gateways. These VNFs combine several characteristics. To summarize what Telco Cloud specific is, or what makes Telco Cloud specific, we can list first that it is high performance, for example, for throughput, jitter, latency, packet per second per core, flow scale. It enables high availability. It is multi-tenant and embeds security. It allows to scale out connectivity and perform service chaining across various types of workloads. It allows the creation of dynamic and tiered logical topologies. It makes it possible to move services and network functions. It provides rich analytics and KPIs, as a telco network should. It makes it possible to map the service QoS to the transport network. And finally, it includes support for MPLS as the transport and service layer, as most of telco networks have been built with MPLS. So in addition to these characteristics, the telco cloud network shall support VNFs, which have potentially high needs in scaling. Tens of VMs across some tens of compute hosts is typical. Tens of interfaces and subnets per VM, hundreds of IP endpoints per network, millions of flows, and millions of packets per second. Telco Cloud is a journey, and there is a sequence in the evolution. The first requirement is that applications and services need to rely on a network using APIs, meaning that there is a focus on application developers. The second requirement is that the network becomes as autonomous as possible. Both requirements leverage DevOps and associated CI/CD technologies, which we will see in another webinar. The network goes through a series of transformations from disaggregation to virtualization and then containerization. The separation of the control plane from the user plane is fundamental to that evolution. It makes it possible to decentralize network services, which could only be centralized before. It also sees a trend to centralize some of the functions at the access. In this pendulum, the final placement of network functions need to be flexible and defined per function, per use case, per slice, as we say. This evolution takes place over a unified fabric infrastructure. In a broader view, telco clouds facilitate the connection of users to their data, as traditional telco networks do, but also things to applications and bots or functions to both bots and functions to AI systems. As I was mentioning before, telco cloud is a journey and it's a transformation inspired by public cloud. Public cloud works because it has a set of well-defined APIs to enable the ecosystem to work. A published and proven set of APIs that work at scale on a cloud stack. Underneath, there is a flexible infrastructure which is designed for developers. Like the infrastructure below our feet, massive investment has been spent so that the city above operates with little care about the underlying systems. And telco cloud is similar. It is a deep stack of infrastructure, core services, applications, and core components starting at layer 0. Transforming this stack to be more agile and offer this API layer requires quite a transformation in order to get closer to what public clouds are, still being specific to the telco world. So let's look at virtualization and things like NAV and SDN. Virtualization has been well described by the ETSI in its well-known NAV reference model. In this model, VNFs and their EMS have their VNF managers, or VNFMs. They consume an NAV infrastructure, or NAVI, which is made of a virtualization layer between hardware components and their virtual view. Those virtual components are computing, storage, and network. Virtual computing and storage are implemented using virtual machines or containers, depending on the virtualization technology being used. They can share the same hardware as they are separated from each other by a hypervisor on the server. The virtual network is an NAVI function that connects virtual computing and storage together on the same server or between servers. The NAVI is managed by a virtualization infrastructure manager, or VIM. VNFMs and VIMs are supervised by an orchestrator in a vertical layer called NAV Mano, Management and Orchestration. Virtualization systems such as OpenStack or Kubernetes cover the virtualization layer and the Mano layer. SDN acts as the virtual network layer of the NAVI stack and is part of the VIM. Ceph is an example of virtual storage. The hardware resources are physical servers for computing and storage, and routers and switches for the network hardware. Each telco will have its own way to derive a cloud stack from the ETSI model and translate that into an actual telco site or POP, where PNFs, meaning physical network functions, VNFs and CNFs connect together through an IP fabric made of leaf and spine routers and switches, and connect to other POPs through a gateway router called the DC gateway router or SDN gateway router. Depending on the type of site in the telco cloud, the actual stack may vary because the number of servers in a data center can be quite different between a large site and a very small site. This is something specific to a telco cloud compared to a public cloud, which is typically made of thousands of servers in a single big site, and there are very few of those big sites. Now, from a virtualization network function, a VNF perspective, virtualization is a process of migrating a network function that was previously intended and implemented on a physical hardware dedicated and purpose-built for that function, and migration to a virtualized function running on a generic x86 infrastructure. We have here an example of the mobile EPC made of several hardware functions, which are ported to several servers. So put together, the servers form a cluster that, as a system, renders the same function as the previous PNF. As you can see, the functions split over servers across an IP fabric need to be interconnected in a virtual network. So SDN is the layer that virtualizes and automates this interconnectivity. To start with, VNF vendors have made their life easy when it comes to virtualizing their PNFs. They take each hardware component and transform it as a software virtual machine, or VM, sitting on a server. A chassis is made of control plane modules, which become control plane VMs. Line cards became line card VMs. All those VMs connect together through an IP fabric, which was the chassis backplane in the PNF. In a second step, or for greenfield VNFs, the VNF is made of a cluster of VMs over a number of servers across the IP fabric, so that the cluster as a system can scale out easily over an NVI. If we take again the EPC example, then a virtual EPC is a cluster of VMs, for example, load balancing, session anchor, user plane functions, control plane functions, GI LAN services, and management plane. This cluster has a north and a south interface. It also has an east-west interface that allows all the VMs to work together as a system, which processes packets going north-south. Each of the VNF vendors have a different architecture, interface, and integration requirements. For example, control plane may be centralized or distributed. It may require strict layer 2 or layer 2 and layer 3 connectivity, or pure layer 3 connectivity, and work without or with dynamic routing. The data plane may work as a virtual data plane traffic across the fabric, which may end up in tromboning traffic. It may have a proprietary encapsulation using static MAC addresses, typically use jumbo L2 frames with no fragmentation, and in general consider the backplane as a flat network. So when it comes to disaggregating their PNF into a number of VNFs, the vendor now needs to take care of the networking, meaning that what was hidden in the chassis now needs to use standard networking. SDN helps very much as it makes things much more simple. Let's look at what SDN is. SDN is the adaptation of two worlds, networking and IT. So from networking, it brings technologies such as highly scalable control plane like BGP, layer 2 and layer 3 VPNs based on MPLS, load balancing like ECMP, and overlay networking, MPLS over VXLAN, for example. The benefits are network scale, resilience, and security. From cloud, it brings physical host virtualization with a hypervisor and workloads, an orchestration system such as OpenStack or Kubernetes, and all working over a common x86 platform with a shared service infrastructure with service automation. So the benefits here are the agility of services, self-service, on-demand services, and elastic scaling. SDN is an evolution of networking built upon BGP as the control plane and MPLS as a forwarding plane. So in an MPLS network today, as you can see here on this diagram on the left-hand side, you have BGP routers that share the routing intelligence between routers. The CE user devices can share the same VPN, isolated from other VPNs thanks to several layers of MPLS. PE routers are responsible for isolating VPNs from each other. In SDN, on the right-hand side of the diagram, workloads, meaning VMs, sit in a host, a compute node, and can share the same virtual network, or VN, over the network. A PE function named vRouter sits inside the host and maps a VM to its VN or VNs. The vRouter connects to other vRouters over an IP fabric called the underlay and create an overlay layer of MPLS tunnels which carry all the virtual networks. If a VM needs to send traffic to a CE router outside of the SDN domain, it can do so through an SDN gateway router where MPLS acts as the glue between the data center and the wide area networks. In the control plane layer, servers deliver the SDN routing services to the hosts. The configuration node takes orchestrator requests for VM creation and assigns the network information. The control node interacts with network elements for VM networking provisioning. The collector node is a real-time analytics engine that collects, stores, and analyzes network elements. Again, the vRouter is the virtualized routing element that handles a localized control plane and forwarding plane working on the compute node. The SDN gateway router is a router between overlay networking and in the compute cluster and the wide area networking. In the LAN or IP fabric, the traffic segmentation is done through label encapsulation tunnels, such as MPLS over GRE or UDP, or MPLS over VXLAN. XMPP is a protocol that has BGP payload to exchange route signaling between control nodes and vRouters. This is another view of a virtualized network enhanced by SDN, where you can see that SDN creates virtual networking between virtual machines, containers, or bare metal servers. It can extend to the wide area network or the telco and also to the public cloud. So as a summary, SDN is a technology that has a centralized control logic and a distributed forwarding. A technology that creates an abstraction of the network. A technology that performs a global optimization. And a technology that brings programmability of the network, which allows automation of operations. Applied to a VNF, SDN can solve some of the challenges that VNF vendors have when it comes to interconnect their VMs together in a VNF cluster. Today, 3 different people need to configure or update information. On the VNF itself, typically VLANs are configured per line card VM, in fact, towards a number of service subnets. On the fabric, these service subnets need to connect to each other, which is another set of people doing configuration on the underlay fabric. Last, connecting outside, routing people need to configure service subnets through VLANs and map them to VRFs. This is manual, complex, and heavy, and it can lead to errors. SDN simplifies greatly everything, since everything now is done as an overlay layer with virtual networks. APIs are used by the orchestration. No VLANs are used. There is no touch point at the IP fabric level. There is no touch point at the gateway level to connect to the external VPNs. Now that you have seen how SDN works, watch the SDN networking playing a crucial role in the performance of the VPC cluster that we have seen before. Here, the VPC design relies on virtual networks instead of VLANs, and forwarding is done by the vRouter. VNs are connected to the SDN gateway for integration with the MPLS backbone, north-south interface. BGP as a service is used for routing between the virtual networks and the VMs, and BFD health check is used for fast detection of a VM failure. Let's talk about some challenges to integrate VNFs onto a server itself. Integrating a VNF in an NFVI can be a complex challenge when it comes to forwarding packets at high throughput, specifically. To achieve high performance routing required by a telco, it is very tempting but necessary to optimize the server platform so that packet handling is optimized. There are many parameters on which the operating system can be tuned on a server. If you take here an example of a NUMA, which is a non-uniform memory access system, which is a server made of two core sockets, two CPUs, each one having core CPUs attached to it, and a memory bank attached for each of the sockets. So on the CPU itself, parameters such as NUMA affinity, CPU pinning, hyperthreading, or number of threads have an impact. The use of single NUMA versus cross NUMA, meaning that when packets arrive, they are processed by the NUMA on which they have arrived on the memory bank relative to that NUMA, or if the packet is moved to another memory bank to the other NUMA socket. Then there will be an impact whether there is a single NUMA or cross NUMA handling of those packets when they are moved and processed by the CPUs. On the RAM, parameters such as huge pages, layer 1 and layer 2 buffers, and DMA related parameters will have an impact. On the IO interface, how the PCI bus is used, how interface bond hashing is used, jumbo frames, or how VM use multi-queue, all have an impact on performance. All these parameters can be tuned so that they eventually become very specific to the use of a particular VNF, which seems contradictory to the will of a hardware layer common to all VNFs, of course. So the minimum distinction can be made between a server destined to packet forwarding and one destined to handle control planes. Still talking about VNF integration challenges, performance is a multi-dimensional topic. VNF requirements are expressed as packets per second, number of flows per second, or number of VMs or containers or microservices. The performance model choice is specific to each telco situation. Having a choice of ways to optimize the processing of packets in a virtualized platform, DPDK versus SRIOV versus SmartNICs versus FPGA versus fixed mode with SRIOV plus kernel mode. Let's look at some of them. The kernel vRouter is where the forwarding plane of the vRouter runs in the kernel and is connected to VMs using a tap interface. The vRouter itself is enhanced using other performance-related features such as multi-queue VirtIO. The second mode would be SRIOV and vRouter coexistence. Some workloads can directly use SRIOV into the NIC, while others go through the vRouter. Sometimes a single VNF can have multiple interfaces, some of which use SRIOV to the NIC. The workloads or interfaces that use SRIOV don't get all the benefits and features of the vRouter in that case. A third mode is DPDK vRouter. The vRouter runs as a user space process and uses DPDK for fast packet I/O. This requires the VMs to have DPDK enabled for performance benefits. And another mode, which is the most recent mode, actually is a SmartNIC vRouter, where SmartNICs are manufactured by vendors such as Metronome, Mellanox, or Intel, and they have programmable NPUs. The vRouter forwarding plane runs within this NIC, and workloads are SRIOV connected to the NIC and benefit from the vRouter services. FPGAs follow the same model as SmartNICs. Another possibility is to use disaggregated PNFs for the data plane forwarding for some heavy-duty traffic, while the control plane is virtualized. An example is the MX, which can process the 4G and 5G user plane traffic on Trio for terabits of throughput. So the VNFs with hardware acceleration may then be compared to hardware-based user plane or on PNFs to make sure that the economics make sense, meaning that the price performance ratio is good. Let's talk about cups and distribution now. Cups has nothing to do with tea or coffee, right? Cups means control and user plane separation. It has been introduced by 3GPP in release 14 for 4G and is native with 5G. Cups separates the user plane functions from the control plane functions and connects them through a control channel, which is called the SX interface in 4G or the N4 in 5G. Of course, this principle can be applied to anything other than mobile packet core, notably the wireline subscriber management. The benefits of cups are such that it addresses the growth of bandwidth by distributing and scaling out the user plane. It also addresses latency requirements for edge computing, for example, by placing the user plane close to end users at the edge of the network, while the control plane stays centralized. The scaling of control and user plane can be made independent, which allows for slicing services. And optimal routing can be achieved by co-locating user plane and routing functions. Cups is an enabler for Edge Cloud. Edge Cloud is a recent race between cloud providers and telcos to get closer to end users in order to deliver new services related to, for example, Industry 4.0, connected vehicles, augmented reality, online gaming, or CDN. In that race, cloud providers leverage their software agility to deliver applications over the top, while telcos leverage their real estate and on 5G technology, which provides much higher throughput, a factor of 10, with enhanced mobile broadband, provides also massive scale for IoT, notably, and provides ultra low latency. So in a telco edge cloud, some of the central cloud resources are distributed further and further to the edge sites. To achieve that, the telco sites are disaggregated as PNFs and as VNFs over COTS servers, all being connected by an IP fabric. An integrated NMV infrastructure made of a control plane and a fabric plane, virtual and physical, is expanded across the network then. Edge Cloud is an opportunity to process user data where it makes more sense from the data point of view, from a traffic point of view, from a latency point of view. Each VNF has its own drivers for decentralization, as you can see on that diagram. But it's not without challenges. How to manage the massive scale and number of sites, which is required here. How to balance the distribution of the VNFs across the network. How to manage mobility of user sessions and applications. So a distributed edge cloud can be a complex system to manage. Virtualization, disaggregation, control plane and user plane separation are all enablers for telco cloud, for edge cloud. They create service and NAVI layers that are deployed flexibly across the network, such as in this example, showing how a 4G and 5G mobile core is deployed in both a centralized and distributed manner. As I said, CUPS is the fundamental technology in the 5G mobile core. The user plane functions, meaning where the subscriber traffic is terminated and routed towards services or toward the internet, is clearly separated from the control plane functions. The control plane uses a service-based architecture where all control functions are decomposed in microservices. This architecture relies on virtualization, more specifically containerization, and scales out over a common IP fabric. The wireline world is also taking the same path. BNGs are being disaggregated using the CUPS model. User plane and control plane functions are being merged under a joint development between the 3GPP and MEF standard bodies. This convergence of wireline and wireless over a single telco cloud architecture will enable a convergence of services and operations. The latest development in the telco cloud journey are about cloud native. So let's have a quick look at what it means. Cloud native is a term that illustrates the adoption of cloud principles following a long evolution of virtualization over the last 20 years. It's now materializing in the Cloud Native Computing Foundation, which has a work group focusing on telco use cases. What does it mean for telco cloud? So cloud native means that instead of deploying a VNF or an application in a monolithic way, where all functionalities are in a single process, each functionality is separated in an autonomous element called a microservice. In order to scale out a VNF, instead of replicating big monoliths, you now replicate each microservice as needed. In the telco cloud world, this translates into VNFs being decomposed into functions that scale out independently. For example, user plane and control plane functions will scale out separately. In addition, any service that can be extracted and made common is now available for all functions. For example, data storage or load balancing here. All these microservices now you use a common data layer, a common NAVI layer, including a common SDN layer, over a common fabric layer. The use of microservices has implications. What was inside a VM is now visible to the NAVI. There are many more events between microservices than there was between VMs. There are many more services per servers. Resources are very dynamic and may not stay on the same server all the time. And a microservice may reload anywhere after a crash. This is today very static with OpenStack. Routing between microservices across a cluster of containers and VMs is becoming now a major challenge, and you may hear about network service mesh. Adopting microservices means accepting architectural complexity in order to gain agility. Distributed computing is complex, and developers face challenges as they transition monolithic applications towards a distributed microservice architecture. An approach they are using is the one of service mesh, and the term service mesh is used to describe the network of microservices that make up such applications and the interactions between them. As the service mesh grows in size and complexity, it can become quite hard to understand and manage. So to address this, Istio is an open source tool that creates an infrastructure layer for service-to-service communication, where the microservices are defined as a mesh of proxies, which are injected as sidecars into each microservice. Being inserted into the microservices and acting as a front end to them, Istio manages the discovery, the load balancing, the failure recovery, the authentication, and the monitoring of the services in a service mesh. An Istio service mesh is logically split into a data plane and a control plane. So the data plane is composed of a set of those intelligent proxies deployed as sidecars. The control plane manages and configuration the proxies to route traffic and enforce policies and collect the telemetry associated to it. Istio uses the Envoy proxy, which is an open source proxy designed for cloud native applications. So these are the latest development in the cloud native journey, and you may hear about all those terms and technologies the more we see virtualization moving to containerization and all the VNFs moved to containerized networking functions. Now you hopefully have a better understanding of what is telco cloud, what NFV, SDN, CUPS, and cloud native mean. That will help you to go through the next webinars. So as a summary, we can say that telco cloud is an ecosystem which involves many actors. NAVI stack distribution vendors like Red Hat, Canonical, VMware, SUSE, etc. SDN vendors like Juniper, Cisco, Huawei, Nokia, and VNF vendors like Ericsson, Huawei, Cisco, Nokia, Mavenir, etc., etc. And hardware vendors like Intel, AMD, HP, Dell, Lenovo, switch and router vendors such as Juniper or Cisco. And also there are many open source projects, notably in the networking stack, such as OpenDaylight, OpenVSwitch, Tungsten Fabric, which is the open source version of Contrail, DPDK, FastIO, Calico, Istio, Envoy, and so on and so on. The role of the Linux Foundation is increasing with ONAP, OPNFV, Acreno, and CNTD projects. And new cloud-native efforts are competing, the CNCF being a major actor nowadays. Telco cloud is a constant evolution, meaning that brownfield is a rule. So thank you for having attending this webinar. This is the end of our module. Do not hesitate to contact the Telco Cloud Solutions team for any question and help. And looking forward to see you on the next webinar.